In this video, I will be presenting the Legendre Transform, which is a transformation that is widely used in physics, both between the Hamiltonian and Lagrangian formulations of classical mechanics, and it also the transformation between energy and enthalpy in thermodynamics. In this video, I will attempt to make this transformation intuitive by making an example involving balloons. So let's start by looking at balloons as our physical model. If we have a single balloon, we assume that the balloon that we are looking at has a certain elasticity related to it, and that every balloon can be described by how big it is, by its volume. And so our physical model is basically just a balloon and how big it is. Now we can think of a space of balloons, so all the possible ways that our balloon can be. And each point on our line, so the same balloon but in different states, so it would have different sizes at every state. So that would be our physical system. It's a state of things that are in a certain way. Now we would like to describe our system in a way that makes sense. So we don't want to just talk about balloons in the abstract. We want to talk about exactly which balloon, be able to say which balloon we're talking about. So we introduce another line like this. If this is the space of balloons, the abstract space of balloons, we can have a line of real numbers, which would be all the volume. So it would be the line of all the volumes. And we can associate every volume to a specific balloon. And so each balloon can be completely described by a volume. And there is only one balloon that has a specific volume. So these things are what we call one-to-one related to each other. And so we talk about the balloons through their volume. Since we can completely describe our system with a single number, this is a one-dimensional system. So there's only one number to completely describe what we're talking about. In general, there can be larger dimensional models. For example, if you want to know where a ball is in three-dimensional space, you would need three numbers to describe this. But in our case, we just need one number, so it's one-dimensional. Now we want to introduce another line. So we're now up to 3 lines, and we will call this line the pressure. And we will say that on this line, we have different values of pressure like this. Say like over here would be 0 pressure, for example. And each pressure can also be related to a balloon by associating the number pressure with how much pressure each balloon has. And so basically what's happening is that we have an abstract space of balloons, all the possible states of a balloon. And now we see that each balloon, assuming that bigger balloons have a bigger pressure and smaller balloons have less pressure, we can see that each balloon is associated also with a single pressure, like this. From this picture, we can choose now to describe our balloons entirely in terms of their volume or in terms of their pressure. What is important is that both of these descriptions are accurate and complete. They give all of the information that we need about our balloons. Now, in physics, whenever you talk about a certain physical system like balloons, and you want to talk about the balloons in terms of their volume, and then you want to shift your description of your balloons to a description involving pressure, we call that a change of variables. And the Legendre Transform, which is our ultimate goal, is one form of changes of variables. So what does it do when we have a change of variables? The fact that we can describe a unique system through 2 different variables, this makes a unique link between each pressure and each volume, like this. So this would be a link between each pressure and each volume. So we would have one volume associated as a function of pressure. If you give me one pressure, then there's a single balloon associated with that pressure, and the volume of that balloon would be the output of the function volume of pressure. Similarly, we can make a function pressure of volume, where the volume tells us completely which balloon we're talking about. And this in turns, this balloon has one pressure, and that would be the output of our function, pressure as a function of volume. So we have volume as a function of pressure, pressure as a function of volume. We have this space of balloons on which we have two different variables. So we have two different variables stuck in a one-dimensional space. And how you can have many variables stuck in a one-dimensional space is when they're dependent on each other like this, that they determine each other. Now we want to see how we can go from volume to pressure in a way that's done typically in physics. Something that's interesting from this setting is that now we can think of volume and pressure as kind of variables that exist on their own, but we can also shift. So if we have volume plus pressure like this, what does it mean? In a single equation, I would say that volume and pressure would be the volume and the pressure of the same balloon, like this. And so the volume plus pressure would be a function of a single balloon. This means that whenever we write volume and pressure together, they're not independent from each other. They're constrained by one another. And this can be made explicit if we say that, for example, volume of pressure plus pressure. And this would be the form of this expression where we make pressure the independent variable and make volume dependent on pressure. But alternatively, we can also do the opposite and say this is volume plus pressure of volume, like this. And then volume is now the independent variable and pressure depends on volume. Now, which one is independent and which one is dependent doesn't actually matter that much because we're always talking about one unique balloon, and that balloon determines completely both the volume and the pressure. So regardless of what depends on what, things are constrained. Two different variables are constrained in a one-dimensional space. Now we want to look at how balloons expand and how we can relate volume and pressure of a balloon. So if we have a balloon like this, we want to look at the energy of a balloon because that's how we will relate volume and pressure. We want to see the work because work is a transfer of energy. So you always determine your energy based on work. Work is done by a certain pressure inside of our balloon. So work is force times delta x, say. It's the force times the displacement. Now, we can picture the pressure inside of our balloon as the force, because it's a force inside of our balloon with some proportionality on area that we can neglect here. And then that's multiplied by a change in position. Here, the change in position would be perpendicular to the surface, and so would result in an increase in the volume of the balloon. The force would become pressure here, and the displacement would become an increase in volume. We are assuming here that the pressure is constant, which is okay for a very small increase in volume. The work itself is a change of energy. So we would have delta U is equal to P delta V. Now, if we make this change really, really small, so a tiny change, we write a D like this. Tiny change of energy is equal to P times a tiny change of volume. So this is important because this is a relationship between pressure. So what is the quantity of pressure? What is the change of volume? And what is the change of energy through this concept of work? Why is this important? Well, let's look at just change of energy. Here we take energy as a function on our space of balloon. So it's a number associated with every state of our balloon. And that's how much energy that specific balloon has. But here we want to make energy a little bit more defined. So we're going to say energy depends on the volume. The energy, U, is the function that takes in volume and gives us the energy associated with the balloon of that specific volume. So if we take this as a function of the volume, then change of that function is equal to change of the function over change of the its argument volume times change of volume. Now here, this change of a function per change of its argument is its first derivative. And so we have u prime, which is still a function of volume, times change in volume is equal to change of energy. And now we want to see that these two expressions match. From the idea of work, we see that this and this must match. These two things must match because they occupy the same position in an identical equation. And so u prime, the first derivative of volume, is equal to p. Now, why is that so great? Well, it's because we remember that pressure depends on volume. And we said that pressure of volume is the arbitrary way in which pressure depends on volume. But now we see that this way, the specific way in which it depends on volume, is the first derivative of volume, if we just take pressure to depend on volume. So pressure as a function of volume is the first derivative of the energy. So let's make a little drawing now. Two variables that we're dealing with, we have pressure and we have volume, right? Now, on the volume, here we have a function, u, the energy, as a function of the volume. And basically, we see that with the first derivative of that function of volume, we have this link. The first derivative of our function gives us the pressure. The first derivative of energy is the link bringing volume to pressure. Now we know that there is another link this way that is volume of pressure, right? This here is equal to pressure of volume. These things are the same. It's just that they correspond, pressure volume corresponds to the first derivative of the energy. And here we have volume of pressure, which we don't really know how it works in relationship to the physics of the balloons yet. But we would like this situation to be kind of symmetric here, because there is no real preference between volume and pressure, mathematically speaking, when we decided to take volume as our main variable. So ideally, we would like this picture to make this picture symmetric. So we would want another function, which we don't know what it is, but let's say it's some other function, h of p here, such that its first derivative should give us volume as a function of pressure. And so the first derivative of h should bring pressure back to volume, should be the inverse direction of our change of variable. So now we would like to find h here. And this idea is really the idea that Legendre transform, because we will say that h here is the Legendre transform of u, this symmetric function which allows an inverse change of variable through its first derivative is the Legendre transform of u. But now we would like to know exactly what h is in relation to u so that we can transform between them easily. Well, the first thing to notice is that h prime, for every volume that is brought to pressure through this arrow, it will be brought back to the same point. Basically, v of p of v has to be equal to v. It's always talking about the same balloon. And so the volume associated with that balloon is the same balloon, and so it's the same volume, regardless if we talk in the middle about its pressure. So the first thing we can observe is that regardless of what h is, we can see that the change of h, and h is a function of pressure, has to be equal to the change of h over the change of pressure times the change of pressure. And we can see that this here is the first derivative of h. So we have is equal to h prime of p dp, right? But now we also see that we would like H prime of P to be equal to V of P, the volume associated with that pressure. And so therefore, we will say that H prime of P is equal to V of P dP. We don't know what H is, but we know that we want its first derivative to be equal to the volume of the pressure, which itself is known. So this is the constraint that we place on H in order to figure out what H is with U, the energy, as our starting point. We look at both dH and du because we want to relate H with U directly, and that would be the difference. That would be the way in which the Legendre transform is special. So dH here would be equal to V dP, right? So here we say V of P dP. We can just write V here with the idea that this volume relates to our single balloon that we are talking about all of this time. And we can make it depend on P at any time we want, or we can make V our independent variable. But for convenience, we just write V. And so here we have du is equal to P dV, like this, right? So just the fact that the derivatives of U and H, like this, were the inverse function P of V and V of P, means that we get these, this structure in the change, P dV and V dP. And these things look very similar to each other. So where have we maybe seen this somewhere? So we're going to introduce another object so that we can link and specifically describe the way in which these two expressions are similar. If we take a function V times P, we introduce this new function V times P. Now this would be a function of balloons once again, right? It would be V times P, and both V and P depend on which balloon specifically we're talking about. But regardless what balloon we're talking about, the change in this function, because we're interested in changes everywhere, the change in this function would be equal to the value of V times change of P plus the value of P times change of V. And this would be true for any product of functions like this. This is the product rule in a different form than in Calculus 1. It's relating the change instead of the derivative. It's the same idea, that you can see that the change of a product would be the equivalent to fixing one of the variables and changing one, plus fixing the second one and changing the first one. So dVP is equal to VdP plus PdV, right? So why is this so great? Well, we see that VdP here is the same, and PdV is this one. And so we can rewrite this in terms of H and U. So we have this is dH plus du. Now it becomes a bit clearer why we want to forget what depends on what to some extent. Because here U is a function of volume, and P would also be a function of volume, whereas here V would be a function of pressure. And so in this formula, it's not clear if things depends on volume or if things depend on pressure. The reality is that it could depend on either, because at any point in time, we're still talking about one single balloon. And so we could make pressure depends on volume and make pressure depend on volume here as well. And then everything is a function of volume. Or we could make the volume depend on pressure. And the reality is that it doesn't matter which one depends on which, because, as I keep saying, it's the same balloon. So here we have basically VdP and PdV, dH, du, right? The change in H and the change in U is equal to the change in Vp, right? So we have this equation, right? This is something that we want to be true about H, because we keep using H, but we still don't know what it is. But whatever it is, we want it to satisfy this equation. We want the change to be related in this manner. So how can we choose H so that this holds true? Well, the easiest way to pick an H so that this equation holds true is to take H is equal to VP minus well, the first thing we can do is isolate DH actually. So it would be to say DH, we send DU to the other side, minus DU on both sides, like this. And then we would get D of VP minus DU, which is also equal to the change of the sum of the functions, like this. And so we get this. The change, this is what we want to be true for H. We want the change of H to be equal to the change of this function. And when is this true? Well, in particular, it's true for a bunch of functions, but one function for which it is true is if we define H to be VP minus U. The energy of our balloon, the volume of the balloon, times pressure of the balloons minus energy of the balloon. This here would make our master equation here true. And so from this, it should follow that H prime of P is equal to V of P, because that was our goal all along, is to find this relationship. It should follow directly. And how can we see that it follows? Well, DH is equal to DH over dP dP. And also, DH is equal to dVP minus U is equal to dVdP. So if we just do it, VdP plus PdV through the product rule minus du. And we know that this thing is this thing is PdV. And so it cancels with this one. And so therefore it's equal to VdP. So DH is equal to VdP from this, but it's also equal to H prime dP. And so therefore H prime is equal to V. So H prime of P is equal to V of P. And so we get the desired relationship for the derivative of H per P. And so basically the H is a thermodynamic quantity, which is the enthalpy in thermodynamics. And the reason why it exists is because if you do a Legendre transform, which is what we have done, you get a view with the change of variables between volume and pressure, you get the enthalpy. So the whole structure, if we look at the whole structure, we would have P and V, and these are related through U prime of P, it would be the other way around. H prime of P, and this would be U prime of V. P of V is equal to U prime of V, and this would be V of P is equal to H prime of P, like this, right? And then the Legendre transform is about, okay, if this is true for U and the correct U and the correct H, how is U of V and H of P directly related to each other? What is the direct transformation between U and H that creates this nice change of variables? And this here is the transformation that H is equal to PV minus U, and U is equal to PV minus H. The second here is can be derived exactly how we derived this here, starting from H instead, since everything is symmetric in this whole issue. And so this is what the Legendre transform is. It's a transformation between kind of higher order quantities, energy and enthalpy, which are themselves only relevant through what are their derivatives. So this is kind of the real world in a sense. And the way in which the higher order things are related in order to make this nice change of variables, this is the Legendre transform right here. And so these higher order things are really just variables whose derivatives give you real information about the real world. And this is true also in other settings, such as in classical mechanics. You can describe a system based on the Hamiltonian, which depends on momentum, or you can, and also position, but we can just focus on momentum. And you can also describe a classical mechanics system through the Lagrangian, which itself depends on, we call it q dot. So that would be the first derivative of position. But it's really just velocity. And so how do you change? So the same system is described by momentum, but is also described by velocity. There is a change of variables between momentum and velocity, which is described by these first derivatives. And therefore, the way in which the Hamiltonian and the Lagrangian transform between each other is also a Legendre transform by the exact same logic. And that is why when we describe systems through higher order variables like Lagrangian Hamiltonians, energy, enthalpy, and we describe a physical system which needs transformation of random variables, it is very natural that the Legendre transform would arise anywhere where we're doing changes of variables. That is the video. Please like and subscribe and hit the notification button. Goodbye.